Hello and welcome back to another LeetCode problem. So today we're going to be doing the problem of the day for June 16th, and it's going to be the number of ways to reorder an array to get the same BST. I think it's actually a really cool problem, and I definitely have to research some math because you're going to use like math that you use in high school for this problem, and so I'm sure a lot of you aren't familiar with it, but I'll remind you of how it works again. And yeah, let's get into it. So given an array nums that represents a permutation of integers 1 to n, we're going to construct a binary search tree by inserting the elements of nums array into the empty BST, find the number of different ways to reorder nums that the constructed BST is identical to that formed by that original array nums. And so pretty much what they have here is, so they have a BST like this. They have a 213 BST, and they are saying, is there any way to reorder the elements 213 such that you can make the same BST? And so this example might not make it clear to you as to why, but the later one will. When you're actually making a BST from an array, what you need to do is you need to take the very first element in the array and you need to make it the root. Right, so if that's the case, if we need this, that means the other elements we have left are 1 and 3. And so we can give it 1 and 3, and if we do that, then we make 1, and where can we put 1? We have to put a 1 over here. And then we can put a 3 here. So we can also do it this way, right? And then that way, we would have the 2 still, and then because the 3 can only go into one place and the 1 can go into one place, either combination is fine. So a 2 followed by 1 3 or a 2 followed by 3 1, either combination is fine, in which case you're returning 1 because you are counting the original, you're not counting the original array as one of your combinations. This is the original one, this is the one other one. Okay, now let's look at the other example, and this one is going to make it much more clear like how things go, and we're going to spend some time on this one. This is going to be the important example to understand the problem. So we have 1, 2, 4, and a 5. And our array now is 3, 4, 5, 1, 2. We're actually going to make this bigger, and we're going to spend some time looking at this. So remember, like I said, we know already that the first node, like whatever array we use, the first node has to be a 3. It has to be a 3. So this already has to be a 3. Now we just have a few nodes to work with, so we have the 4, 5, 1, 2. And so our array is always going to start with this situation. Now we just have to figure out how many combinations of this can we have. And this is the first one. Now, the way this works is, I'm going to explain it. The way this works is for a path, like let's say this is a path, and so on. The rule we have to follow for a binary search tree is for a path, we have to make sure the nodes are the path are processed in the same order. Otherwise, there's no way to like have these same binary searches. So for example, this path, 4, 5. That means that nodes 4 and 5 have to be processed where 4 comes before 5. Okay? So it has to be like this. And then this path, 1 comes before 2. And then the other stuff doesn't really matter, and I'm going to show you why. So let's say we have some combination. So remember, 4 has to come before 5. So let's just say we have 4 comes before 5. Now we have 1. Now we have 5. Then we have 2. So what's that going to look like? Well, we're going to put in this 4. 4 can only go into one place. Now we're going to put in the 1. 1 can only go into one place. Now the 5. One place. And 2. And so notice that's the exact same tree because we followed our rules, because for a path, 4 comes before 5 and 1 comes before 2. Now let's try another one. So what about 4, 1, 2, 5. Okay, well, we have this 3 again. So we process 4, we process a 1, then we process a 2, then a 5. And so that works again, right? So that's another combination. Now, 4 does have to come before 5, but it doesn't necessarily have to be the very first element. So let's just try putting a 1 first. And so now let's just say we have 4, we have like this, right? And so because this also follows the rules, I'm going to draw it over here on the left. So we're going to have the 3 again. we're going to process a 1, process a 2, only one place. For all these nodes, they can only go into one place. 5. Same thing. And now let's find some more. So what about 1, 4, 2, 5? Did we do that yet? I don't think so. Okay, I'm going to put that over here. So 3, we have 1, 4, 2, 5. I think we have 1 left, I believe. So we're going to have the 1. Do we have one more? Maybe we actually don't. I don't know. We have a 1, 4, 5, 2. Maybe we missed one, but you kind of get the point. So this is the last one we're going to do. Now we're going to put it up here. So 3, same thing. So 1, 4, 5, 2. Okay. And so you can see it's gonna be the same. And I do think that is, so that's 5 different ones plus this original. So that's 6. Maybe we missed one. No, that looks like it's right. So remember, so you can see in this example, they always have to start with a 3. So we know the 3 has to be the root, and then we just have to take care of the rest. But how do we actually do this for something bigger, right? Like, that's going to be a problem. How do we do this for something bigger? Well, it's actually going to be a recursive problem, and I'm going to show you how. So let's say we have this 3, 4, 5, 1, 2. So now remember that the nodes on the left have to come before the nodes on the right, but they don't necessarily have to come in the same order. Like in this example, they did, but, and also, by the way, so you can notice in this picture, because there's only one path, there are no other orderings. Because there's only one path here, these nodes have to come 1, 2, and 3. So there's no other way. But so what we're actually going to do is we know that like the root has to come first, right? And so when we have this 4, 5, 1, 2, it's actually going to be a subproblem of we can just take the nodes to the left of the root and then the nodes to the right of the root. So for example, we are going to split it up into 1, 2, 4, 5. And then this is a subproblem, right? So if we know how many combinations are each one of these and each one of these, then I'm going to show you what you can do. And yeah, you can't just, like, it's not necessarily the nodes to the left have to come in a strictly this order, because you can have trees like this where you have a tree and then you have a child and then you have 2 children here. And so it's really, like I said, the nodes on the same path have to come in order. So like nodes on this path have to be like node this one, and this one. But just because the nodes are to the left of the root or something, like they can, so these nodes can come in any order. It doesn't matter. So it can either go 1, 2, 3, 4, or 1, 2, 3, 4, and so on. So we're going to divide this down. Every time we have an array, we're going to divide it down to a subproblem. And then once we have a subproblem, it's actually pretty easy. So the way these combinations work is like, let's say we get some number for how many combinations are in here and how many combinations are in here. And let's figure out our base case, by the way, for that. So let's say we do have this 1, 2. Well, if we have a 1, 2, if we have an array of 2, remember the root has to come first. So if the root has to come first, there's only one way to do that, right? And so when our array is length 1 or 2, that means our number of combinations is going to be 1, right? If there's only one element, obviously it's going to be 1, and if there's 2, the root has to come first. So now that we have this base case, and we can also divide our stuff down, let's figure out how many combinations there are. So remember, the root has to come first. So when we have like this 3, 4, 5, 1, 2, we can just take out the root and just say like, okay, how many combinations of lefts do we have? How many combinations of rights do we have? And then it's just a subproblem, and it's pretty straightforward. And pretty much it's going to be like this. So we have 4 slots total for this whole thing. And now this, like, there's going to be some combinations here, but if you think about it, if you look for something like this, these 2 elements have to occupy 2 out of 4 slots. So like, let's say we put them here and so on. We can put them wherever we want, right? So wherever we put them, then the other elements have to occupy the other 2 slots. But the subproblem of if you have n elements, or if you have k elements, and n slots, the subproblem of like how many different ways can you put these k elements in these a slots is actually the high school math problem, and it's n choose k, and I'm going to show you like the actual like math for that. But there is also a nice thing about Python is there's a function that does this. I was trying to do this without it, but it ends up taking a lot more space. So the two things we need are we need the number of combinations for the left and the right. And then once we have that, we need to figure out like how many total slots do we have. And then as soon as we put, like, let's say we put in a left element here and a left element here, now we know wherever we put the left, the rights automatically have to be in the rest. So the subproblems just figure out like all the different ways you can put in left elements in the total elements you have. And also figure out how many different ways can you have these left elements and how many ways can you have these right elements. And so our final solution is going to be the number of combinations for the left times the number of combinations for the right times this n choose k, where it's going to be like this. And so hopefully that makes sense, because like, let's say we can put these left elements, you know, like let's say you can put these like 8 different ways. Well, if there's an L and an L and a right, then the total number of combinations for this whole thing is how many different ways can you order these left elements times how many different ways can you order these right elements times how many different ways can we actually put down these left elements in these boxes, right? So the number of combinations of L is like if we have, you know, like L1 and then L2, or do we have L2 and then L1 and so on. And for the right, the same thing. So if we could have something like this, maybe this could be a solution that would be valid. Then we can have something like L2, L1, and then we could have, you know, R2, R1, and so on. But we're going to figure that out in these subproblems. And then once we get these like subproblems, then for this whole thing, it's going to be the combinations of the number of ways you can order these lefts, the number of ways you could order these rights in just, you know, like if you just take these array of left elements, how many different ways can you do this, right? So this is this subproblem. Then this subproblem is how many ways can we order the rights, and then this boxes thing is like the n choose k part. And so that's just if you have n slots, how many different ways can you put k elements to fill these n slots? That's going to be that. And so I'm going to show you the code, and then I'm going to show you kind of what I did, and then the optimization that you can make in Python. And I think if you're coding in another language, it might be a little trickier for you. So let's start coding it up here. And first what we're going to do is, and I'll actually show you quickly what I did. So for this n choose k, by the way, the formula is something like, so for n choose k, I'm just going to write it real quick and show you what I did. And then like, I realized that it was just taking up a lot of space, and I did have some errors when I was trying to make this number smaller. So first of all, we're gonna take this, these numbers are going to get really big, so we are going to have this mod thing. And we are going to add 7, and then we're going to take our output, divide by that. But so what I actually did was I made a dictionary for factorials, because n choose k equals, let me get this formula here. Okay, it's n factorial over k factorial times n minus k factorial, which is this whole thing. And so this n can be really big. This n like can be 1,000 elements. And so when you have, like, if you just type in 1,000 factorial, it becomes like a huge number. So even though I could calculate these factorials reasonably fast, like what you could actually do for factorials, you could say something like this, but I'm going to comment this out because I ended up not using this code. You could just say like facts I equals facts I minus 1 times I, and then you can have some initialized like factorial, like, you know, maybe let's say you initialize 1 to 1, and so like the factorial of 1 would be 2, and then the factorial of 2 would be like factorial of 1 times 2, and so on. So this is kind of like the way to get factorials really quickly, where we're just multiplying by one number instead of recalculating all of these. But once again, this number gets really big, and I did try to mod it by this to make it smaller, but then my outputs were incorrect. So I don't think you can, like, if you try to mod before the very end, you might get like some wrong numbers. So I wouldn't suggest using this, and I'm just going to comment this out, and then I'll show you how to do it in Python, like in a more efficient way. But in another language, I don't know if there is, because Python is really nice with like data and stuff, and so it has a lot of functions like this. It actually has a function to calculate combinations without storing factorials, which is convenient. But anyway, let's comment this out as well. Okay. But yeah, if you are coding in another language, you would have to store factorials, I'm pretty sure. Or like a Pascal's triangle type of thing to get the n choose k. Okay, so let's also look at the actual recursive function. So it's going to be just like we can call it dp or something. And it's going to take a tree, which is basically the array. And so remember our base case. So if the size of the array is 2 or less, there's only one way to put those nodes, because the first node has to be the root. So if the length of the tree is less than or equal to 2, then we're going to return 1. Now we are going to have the left and the right subtree. And what you can actually do is we can just do a list comprehension here if you wanted to, or you don't have to. And you can literally just say like n for, or actually let's just do it this way. So we can make a left and a right, and then we can do something like this, and we can just go through the values in the tree. But yeah, you could do a list comprehension as well if you wanted to. So if value is less than the root. So remember the left nodes are less than the root, and then the right nodes are greater than the root, and it's a binary search tree, so all the integers are distinct, so we don't have to worry about like getting a duplicate value or something. The tree 0 is always going to be the root. Remember in the array, whenever we pass the end of the array to this function, this first element will always be the root. So if value is less than tree 0, then we can append it to the left array. It's going to be value here. And then if value is greater than tree 0, then you can append it to the right. Okay, and then we actually need the length of each of these arrays to do our actual calculation. So let's do that. So let's do like left counts or something equals length of left, right counts equals length of right. But yeah, this problem just basically boils down to like, can you figure out combinations, and then can you see that that this thing is what you need to be doing? Like once you put in these lefts somewhere, the rights just have to go in every other slot. So the only thing you have to figure out is how many different ways can you put the lefts in, and then how many different orders can you have the lefts in. So it's like how many different orders can lefts be in, right? Like L1, L2, or L2, L1, or whatever, if you have a bunch of them. And then how many different orders can the rights be in, right? R1, R2, R2, R1, whatever. And then this n choose k is where the left and the rights actually go. So it's those 3 steps. Okay, and so we're going to actually write down this equation now. So we're going to return, and it's a long one. So DFS of the left. So we're going to, this is DFS of the left is how many different ways can the lefts be ordered in, right? Like will it be L0, L1, L2, or what like how many different ways are those can be ordered in, times DFS of the right. How many ways can the rights be ordered in? And now here's this n choose k thing that in Python it's called comb, and then you can pass in an n and a k. And so the n is the total number of spaces available, which is just going to be the left count plus the right count. And then the k is going to be the left count or the right count. It doesn't actually matter, because for this equation, like let's say we can look at this problem, right? So let's say left is 2 and right is 3. Our equation would then be, so n would be left plus right, so it'd be 5 factorial over, let's say we used left k here. So actually what would happen is k and n minus k would be no matter which one you picked, it would be one or the other, right? So let's say k would be the left here, so then this would be 2 factorial, and then n minus k would be 5 minus 2, which would be 3 factorial. But if you pick the right to be k, then it would be 3 factorial, and then n minus 3 factorial, so it would be 2 factorial either way. So it doesn't really matter. Either one would give you the same solution if you put a left count or right count here. Okay, so now we return that. So this actually should be called dp. Oops, dp. Okay, and yeah, and then after that we can let's see here. Return dp left, all this. Okay, so now we actually have to call the function. So we have to call return dp tree. And then remember that, so this will give us the combinations, but remember that one of them should not be included because like this one's already given. So one of the combinations will be this. So we need to subtract 1 And then yeah, this is the number that's going to be the really big number, and here's where we need to mod it. And if you did like, yeah, when I tried, like I was trying to debug when I made this factorials, I did something like this, and then I wrote like something like this, and then this gave me bugs, and I wasn't really sure what was going on, but it's because I modded too early, and then my math was like incorrect. Definitely, yeah, problems with math are, you know, kind of annoying, but it is what it is. Okay, so dp tree -1, and then this is where we actually mod it by this. So let's see what we screwed up. So this should not be tree, this should be nums. Okay, dp. Yeah, I actually called it DFS before. And this should be count. Okay. Okay, so hopefully that worked. And yeah, so as you can see, this beats like 50%, but when I did it with my factorial, it was only beating like 10%. I don't know if I can see. Maybe I can show you one of these. Yeah, so this was 83 megabytes, and this is 20. So storing all the factorials is definitely, you know, not ideal if you have this comms function. It definitely saves you a lot of space. But it's still doable. Like if you did do this factorial thing, it would pass. You would just not have this. Because in Python, you don't have to worry about overflow, but I think in another language, you would have to probably do something else. Okay, and let's think about the space and time here. It's going to be kind of tricky, I think. So what are we doing, and how long is it going to take? So every time we're splitting our array into like 2 different arrays, pretty much. And so this should, I think this should go through. Let's think about this actually. We are splitting our array. I think it would actually go like n times, I'm pretty sure, because we're gonna have to split our array until we get like elements of 1 or 2, which would technically be n. Yeah, I think this would be O of n. For like the splitting would just be O of n. And then space. So worst case scenario, our recursive call stack is something like this, where we have to go all the way down, which would be O of n. Well, actually, sorry. Yeah, that would be an O of n call stack. But then also we do keep splitting the array, and we keep passing that down. But because we keep splitting it and we keep passing that down, I think that's fine. Yeah, so I think this is O of n for space, I'm pretty sure, because of this recursive call stack. I could be wrong, so if someone wants to double check that, feel free to do that. But yeah, that's all for this problem. And yeah, honestly, once you understand like this combinations thing, how it really works, it's not super hard, but it's definitely not super intuitive to get this combinations, especially if you haven't done these like, you know, put elements in spaces type of thing, and probably like I haven't done it in years, so I'm sure a lot of people are like in the same scenario. But yeah, hopefully you enjoyed this problem, and if you did, please like the video and subscribe to the channel, and I'll see you in the next one. Bye.